Welcome back for the afternoon session. So today afternoon, we are having two prep talks. The idea is that all these talks are given by PhD students or postdocs, and they are supposed to be sort of background talks, which means we hope you interact more during these sessions. So the first talk, prep talk, is being given by Abhinandan Das. He's going to be speaking on localizations in homotopy theory.
Thank you, Rekha ma'am, and thanks to the organizers for this opportunity. So this is localization. So this is localization in homotopy theory. So first, we start with localization in commutative algebra. So what is that? Is if we start with a ring R, which is commutative associative and unital, that is as a unit. And if we take S a multiplicative set, that is a subset of R which is closed under multiplication. Then we can talk about S inverse R, which is essentially inverting the elements of S in R. So this is defined to be pairs like S comma R such that small s belongs to this multiplicative set. Okay. Yeah. So this is nothing but small collection of small s comma R such that small s belongs to this multiplicative set, small r belongs to the ring, and an equivalence relation which is defined like this. So if S1 R1 is called to be equivalent to S2 R2 if there exists an element from S called T such that T times the cross multiplication, say S1 R2 minus S2 R1, this is 0. So we'll denote these pairs for convenience like R by S. So S is inverted in S inverse R. And we can see S inverse R becomes a ring. Where multiplication R1 by S1 times R2 by S2 is same as R1 R2 by S1 S2. And we have to check the equivalence relation holds, but that works. And any element of R going to R by 1, this is a ring map. We can also take M. So let's look at few examples. So if I start with the ring to be ring of integers, and if I take S to be the multiplicative set, generated by primes which are not a particular prime P. So let's say generated by primes Q. These are primes which are not equals to a particular fixed prime P. Then this S inverse R is denoted as Z localized at P, this P. So we are inverting all the elements which are not a multiple of P. So, and if we take S to be R minus 0, so then we will invert all the elements which are not, so here R is Z, so you will invert all the elements other than 0. So we will get Q. Rational numbers. If I take M, we can also talk about localization of modules with respect to this multiplicative set. So if I take M and R module, then similarly S inverse M is defined as this pairs small s belongs to capital S and small m belongs to capital M with similar kind of equivalence. And then we can see this is a module over S inverse R. And then we can also note that this S inverse M is nothing but M tensored with S inverse R over R. So M is an R module and S inverse R via this map is an R module and S inverse M is nothing but this tensor product. The example is if we take A, an abelian group, so that is nothing but Z module and if we take S to be this multiplicative set generated by primes which are not P, so this is let's say generated by Q not P, then this S inverse A is nothing but via this A tensored over Z with Z localized at P. So what we see is we get a functor for abelian groups which is the localization functor which is nothing but tensoring with, so let's say P localization functor is nothing but tensoring with Z localized at P. And then we have series of functors from top star reduced to abelian groups which are nothing but this homology functors the top star is the pointed topological space, categories of pointed topological spaces. And then one can ask, can we get a P localization like this in top star such that this whole diagram commutes? And it turns out this is true for a certain class of spaces, so called simple spaces. So this is actually more generally true for nilpotent spaces, but let's not go there. So this is true for simple spaces. So what are simple spaces? Simple spaces are such that the fundamental group is abelian and the action of the fundamental group on the higher homotopy groups is trivial. So for example, we can talk about simply connected spaces. So pi1 is 0, so the action is trivial. Or we can take H spaces. So examples are simply connected spaces or H spaces. So let's see how this works. So the first thing to look at is where does this image of this functor lie? So that is our definition. Is local spaces. So space X, which is simple space, is called P local if the homotopy groups are Z localized at P modules. So homotopy groups of X. And we say a map from X to XP, where XP is a P local space to be localization, P localization if, so similar thing what happens in commutative algebra happens also here, is that if we have a map from X to Z, which is another P local space, then this map factors through this X, this map, this localization map. And this factorization is unique up to homotopy. So map to any P local space will factor through the localization. But then what we wanted is to have such properties for homology groups, but the definition is in terms of homotopy groups. So the next theorem will link these two concepts. Is so this theorem says if x to xp map L of simple spaces, then the following are equivalent. That this map L is the P localization. So has then in particular XP is P local, and any map to P local space will factor through this map L. That is same as saying L induces a map in homology level, and this is nothing but the localization of this abelian group. So this map is P localization for abelian groups. And 3 is the same holds true for homotopy groups. Is the induced map on homotopy groups so the base point of xp, I'm calling it as x small xp. This is also P localization map. So this theorem actually says that what we wanted is, even if we have started with the homotopy groups to be ZP modules, this diagram works under this theorem. So let's see few examples of P localization for spaces. A topological space. So pointed topological spaces. So I'm not. So essentially, what we no. So I ideally we will be working in the category of compactly generated weakly Hausdorff spaces, but let's not go there. We can take the spaces to be homotopy equivalent to CW complexes if you prefer. That's not a requirement. No, this is. Yeah. This one. This one. Yeah, this commutes in topological spaces. But this map, the uniqueness part is up to homotopy. The uniqueness of this factorization. So I this P local space definition? XP. No, I'm saying, so I'm saying if a map like this, where the target is a P local space, when is that map is the localization map. So we wanted to define what localization is, right? For any space X. So when this map is a localization, and that is what I'm giving. This is P localization if this diagram works. Map to any P local space will factor through this, the P localization, ideally. So like that happens in commutative algebra. Yes. Well, let's see one example. So this is the P localization of spheres. Yeah, so this is for n greater than or equals to 1. So how is this defined? So I will just draw a diagram. So this is by this mapping telescope construction. So what is this is, so we take this, so for convenience, I'm drawing S1s, but we take this cylinders on Sns and then keep on doing it. And then we identify this Sn to this Sn under a map F alpha, which is of degree alpha, and where alpha belongs to, so alpha is not a multiple of the prime t. So I will keep on changing alpha, which is not a multiple of t, and I will just take on identifying this essence by a map of degree f alpha. So okay, let's say this is f alpha 1, f alpha 2. So let's say alpha 1, alpha 2, alpha 3, and so on is an enumeration of this set. This z minus pz. And then we'll take this cylinders and identify the boundary essence by maps of degree alpha s. And doing that, if I take So what this total space is going to be, so I call it space X. And then this inclusion of this first Sn to X if I look at this map in homotopy groups, so pi star we see pi star of X is nothing but this colimit of this diagram, this pi star of X to pi star of X multiplication by alpha 1, then pi star of X multiplication by alpha 2, and so on, which is exactly, so this is colimit of this diagram, and this is exactly equals to pi star of X localized at P. Pi star of Sn localized at P. So we see this under that, under this theorem, under this third equivalent criteria, this inclusion map is nothing but the P localized. And then this one, yeah, this is equals to the colimit of this diagram, which is pi star of X to pi star of X to pi star of X, where the maps are multiplication by alpha 1, alpha 2, corresponding to this degrees of the maps F alpha 1, F alpha. Oh, sorry. Yeah, sorry. Yeah. Sorry. This is pi star of Sn. Yes, sorry. Yeah, this is the colimit of this diagram, and that is the P localization of pi star of. And after we have this P local spheres, we can actually do P localization of simply connected CW complexes by skeleta by skeleta. So I changed the enumeration. Yes. So yeah, even that universal property says if I have another guy says that there is homotopy equivalence. So using this P local spheres, we can actually P localize simply connected CW complexes. But for simple spaces and even for the proof of this theorem, this whole construction actually goes through Poshnikov tower. But just to make this functor work, instead of taking CW complex, skeleta by skeleta, we have to take the Poshnikov tower and then do in each Poshnikov section level. this. This is my definition of P localization of a space. Even if I take the enumeration different, I take this map in homotopy groups to be the P localization in homotopy group level, right? Right? And then this theorem says that that is the P localization. So what we get is a homotopy equivalent guide to if I change the enumeration. If we change the enumeration, we will get another such guide, right? Which has that same universal property. Because on the homotopy groups, it gives this. And then using the theorem and the universal property, we can say those two are homotopy. Okay. Better to take, okay, so, okay. Yeah. Okay, I will, okay, for, yeah, that's point. So, okay, I will change the definition. The simple spaces, I will take, these are homotopy equivalent to CW complexes. So CW type. Then there is no problem, right? Yeah, so one thing is, if we see universal coefficient theorem, this implies that if we look at the homology groups with Z localized at P coefficients, then that is isomorphic to the P localization of the homology groups with Z coefficient. Tensor over Z with Z localized at P, because the dot terms vanishes. So in fact, so that says in our construction, I mean, we didn't construct, but if this, assuming this functor, this space, not only this space is P local, this map actually induces isomorphism in Z localized at P coefficients. So with that observation, I will just, we are going to move our focus to localization of spaces and spectra with respect to homology theory. So Adams, due to, I mean, for his work on Adams spectral sequence, I mean, wanted to get localization of spaces with respect to homology theory. So what, and then Bousfield proved that. So what exactly do I mean by that is, if H star is a homology theory, Then Bausfield constructed a functor LH let's say on spaces for now. Such that there is a map for any space X, there is a natural map from X to LHX, which is isomorphism under this particular homology theory. So as we saw there, so as an example of this is what we saw the P localization of spaces is, so P localization of simple spaces are nothing but are same as this localization with respect to the homology theory with Z localized at P coefficients. So that is by universal coefficient theorem, as we see. And then like localization of spaces, we can talk about completion of spaces. And then it turns out completion of simple spaces is same as localization with respect to the homology theory with coefficients coming from Z mod PZ. Yeah. Oh, no, this happens for full tops. It agrees with our definition for simples. Our case is only defined for, I mean, I didn't say that, but it is only defined for simple spaces, maybe a bit generally to nilpotent spaces, but yeah. Yeah, so, and I wrote localization of spectra with respect to homology theory. So, Bausfield also proved the existence of localization functor in the stable homotopy category. So I will just say a bit what is stable homotopy category. In the category of spaces, there are quite a few stable, what should I say, occurrences like the suspension isomorphism for homology and cohomology theory. And then if you look at the stable homotopy groups, that also has a stable criteria. So by stable, I mean it somehow behaves well with the suspension of a space. And then one wanted to get some category which includes the topological spaces and maybe a bit more, where this, in top we have this suspension and loop space adjunction, and one wanted to get a category where this actually gives a adjoint equivalence. So in particular, these two are equivalences of categories. So stable homotopy category. And that is how we land in stable homotopy category, is where this suspension and loop adjunction is actually equivalence of this category, stable homotopy category. So what are the objects of this category? The objects are called spectrum, in plural spectra. The morphism between two spectrum X and Y is actually denoted like this, which is an abelian group. We have, as mentioned, we have this suspension omega adjoint equivalence. There is a functor from, so this actually comes as homotopy category of spectra, which I'm not going to say. So we have a functor called suspension spectrum from top to the category of spectra. This homotopy, stable homotopy category is a closed symmetric monoidal category. Where the monoidal structure is given by this smash product, and there is internal Hom. So although these are derived ones, I'm just writing it like this. And the unit is called sphere spectrum, which is nothing but the suspension spectrum of S0. So under this suspension spectra, unit is this sphere spectrum. And this is also a triangulated category. Okay, so closed, so monoidal category means there is a notion of product in the category, which is, so there is, so given two objects from the category X and Y, we have a notion of X tensor Y, which is like the product, which is natural in both X and Y. So that is the monoidal part. For topological spaces, it is X cross Y, even for top star. No, even for top star, it is smash product. For topological spaces, it is X cross Y. If it is unbased. Yeah, in this category, this is also, this is just a notation. This is smash product. I'm not defining it. Yeah. It's, I mean, there is no meaning other than, I mean, at this point, we are not taking any explicit guy for smash product. No, no, no. This is not the smash. Yeah, it's just a notation for some product in the category. Yes, and this category also has a triangulated category structure. Where the exact triangles are nothing but the cofiber sequences in this category. And then the triangulated structure and the monoidal structure behaves well with each other, which means the tensoring with an element is an exact functor, so it preserves the triangles and so on. So I just needed this to be mentioned. And one more point is, given any object in this category, let's say E, so this is a spectrum, this actually induces a homology theory E star on spaces and even on spectra level. Yes. Okay, this, so the objects I'm calling as spectrum, again, I'm not explicitly saying what they are. No, I mean, there is, no, here they are different. It's not spec of Earth. Yeah, it's not, okay, the notation might be a bit confusing. That's no, it's not spec of Earth. It's just the objects in this category, stable homotopy. Yeah, so this is, yeah, so this comes as a homotopy category of this category SP. Again, there are different choices of SP such that all these things happen. So there is big story here also. I mean, how the whole thing works. Yeah, so why we need this is because of this, that any such object in this category actually gives us homotopy theories. And what we will do is we'll localize with respect to this guys, this is, because they will induce the homotopy. So if I wanted to talk about localization with respect to E star, what we'll define is localization in this category with respect to the object E. So that is why I am talking about these things. So any spectrum gives a homology theory, and so one such homology theory we know is just an object from this category. Is spectrum means this is an object in this stable homotopy category. It's just an object in this category. Again, I'm not saying how they induces, but they actually induces homology theories on spaces and even on this category itself, on spectrum. yes, as Samik has said, there will be a talk about this in details later. But again, we don't explicitly need what they are, just to define, just to say what we are going to do. Is that so? We have a homology theory, which is the singular homology with respect to an abelian with coefficients coming from the abelian group A. And it turns out this actually is induced by some spectra, which is called Eilenberg-Maclaurin spectra. So this sound familiar. This may sound familiar because the ordinary cohomologies with coefficients from A are given by the Eilenberg-Maclaurin spaces. So in this case, there are guys HA which will induce the homology theory with coefficients coming from A. And then if we wanted to talk about, let's say, P localization, what we really wanted to talk about is localization, let's say, with respect to, so ideally localization with respect to HZ localized at P. But then we'll see what happens. So right now we are going to concentrate on localization with respect to this homology theories coming from spectra. Like for example, this HZ localized at P. Now X2HA will give us, I mean, the cohomologies are given like that, not the homologies. Homologies, not the homologies. So, okay, I'll just say, so there is, so we had this unit sphere spectrum. So if we look at sphere spectrum, that induces on topological spaces the homology theory, which is stable homotopy groups. But I said they actually give homology theories on spectra also. So on spectra level, this homology theory is nothing but is called the homotopy groups of the spectrum, corresponding spectrum. And then this, okay, I'll just say this E actually gives this homology theory E star, which is defined like this. So this is this homology theory, and we have this smash product, and then this is defined like this. But we don't need the explicit thing. Yeah, so we'll look at definitions. So if we localize with respect to the spectrum, where do we land? That is first question. So these are, so let's say E is an object in the stable homotopy category, and the induced homology theory is E star. Then first, a map from X to Y between two objects in this category, F, is called E equivalence. if this F star on the induced homology theory, if F induces isomorphism on this homology theory, E star. So if F star is just this is just E star x to E star y. And this is an isomer of abelian groups. So this is called E equivalence. And a spectrum A, so an object in this category is called so like for spaces, acyclic guys are nothing but whose homology groups are 0. So A is called E acyclic if E star of A is 0. And 3, so if we can define localization with respect to the spectra, so where does the image of that localization lie is this E local guys. So Z is again, Z is an object in the stable homotopy category is called E local if for all A which are E acyclic, this maps from A to Z is 0. And not only that, actually maps from suspension A to Z are 0 for all suspension, for all stars. So if star is negative, I mean that suspension inverse is nothing but loop. So few examples of, let's say, E acyclic guys are, so if I take this suspension spectrum of RP infinity, so 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 example is, so if I take suspension spectra of RP infinity, that is going to be HQ acyclic. Because if we look at the HQ star of the induced homology of HQ on suspension of RP infinity, that is going to be the homologies of RP infinity with Q coefficients. So like for spaces where the homologies are concentrated in some particular degrees, there are guys in this category also, which are called mood spectrum, whose again their homologies are concentrated in particular degrees. So any such mood spectrum MA So the notation for such mood spectrum is MA, where A is a finite group. So in particular, that means the homologies of MA is same as A at 0 and 0 otherwise. Then these guys are also HQ SIQ. And the proof is universal coefficient theorem. So either the tensor vanishes or both the tensor, the tor guys and the tensor guys vanishes. So there is a version of universal coefficient theorem for spectrum also, like for spaces, and that is the proof of this. And now localization localization is nothing but localization with respect to the mood spectra Z localized at P. So what do I mean by localization with respect to a spectra, and does that even exist? And that is where this Bousfield's theorem comes into play, which says this localization with respect to spectrum exists, and they have the properties like we have for topological spaces or even in commutative algebra case. Okay, I shouldn't have rubbed this. So this is the main theorem is due to Bousfield. Is that he proved there exist so for E a spectrum there exists functor LE from stable homotopy category to itself, which is idempotent. So LE of LEX is equivalent to X. There is a natural map from LEX to X. Okay, so the zeroth guy is for any X, LEX is E local. LE is the okay, so LE is the functor, stable homotopy category to stable homotopy category. Oh, I didn't write. I did write LE. Okay, yes, sorry. What am I? Yeah, like localization, I have map from X to LEX. This is like for spaces, this is nothing but a E equivalence. So this functor image lies in the local guys, and this is, if we localize twice, we will end up once localization. And this is an E equivalence. So this actually has this, so this what makes is not equals to identity. If I is yes. Oh. So the first guy is the image lands is E local guys. Yeah, so for example, if I so yes, that is what I'm going to say. So if I have mapped to any local guy, so this is E local, then it actually factors through LEX, like the localization. And this factorization is unique up to homotopy. So this actually has this universal property. And then, as I said, if we localize with respect to the mood spectra MZ localized at P, that is what we are calling P localization. But then here I said that so in particular, the reduced homology with respect to coefficient Z localized at P actually corresponds to HZP, HZ localized at P. So, and Bau's field also proves that this P localization is the correct, it agrees with what we started with earlier, that, so this is one more. Yes. So this is that if I take X, and so the X is a spectrum, an object in the stable homotopy category. And if we look at E, which is also, so this is going to give us the homology theory. So maybe not in generality. So let's say if X is a spectrum plus, so I wrote there is a homology theory pi star, so a notion of homotopy groups on the spectrum. So such that if the negative homotopy groups of X are 0 or are less than 0, then Bau's field proved that localization with respect to HA is same as localization with respect to MA. So H. So this in fact says that instead of localizing with respect to Eilenberg-Maclaurin spectra, we started localizing with respect to mood spectra, and on such guys, so these are called connective spectra. they do agree. And this is not very far from the spaces case, because see, this suspension image of the suspension spectra from top star to stable homotopy category, let's say to spectra, this actually lands inside the subcategory of connected spectrum. So the spaces scale actually is handled under all these things. Yeah, so now okay, so I will just mention one thing is this was mentioned in Srikanth's talks today, is the dual notion of localization is called cellularization. Like we saw earlier, just the lecture before this, is CW approximation, the cellular approximation functor. So it's just okay. This cellularization was first developed by Dror Farjun, and this is the dual notion of localization. So, okay, so cellularization is if this X, so here. We prove this cellularization functor exists, which is, so let's take A is a spectrum, and then this CWA A and X are spectrum. Then CWA of X is like the best, like he said, is the best approximation of X by guys which are built from A. So there is a natural map from CWA to X such that, so the dual notion of local guys are called cellular guys, so such that, so this is a cellular and this map is a coequivalence. So what do I mean by coequivalence? So that means if I consider this map from, see, so this map induces a map to the mapping objects, right? And this is a weak equivalence. So this is the definition of a cellular, a coequivalence, and a cellular guys are such that, so these are such that for all f from x to y, which is a coequivalence, f lower star from CW A. So let's say, so some spectra Z is called acellular. If for all coequivalence, the F lower star from this mapping spaces gives an weak equivalence. So here, the A is for all A coequivalence. So if you start with a coequivalence, then yes, the map on the function spaces will give us weak equivalence. Yeah, so just one example of cellularization. So we saw many examples last talk, but in topological spaces case, so if I take A to be S naught, then CWA of X is nothing but the cellular approximation of X, CW approximation of X. So one example for topological spaces is nothing but the cellular approximation function, CW approximation function. And I guess this is where we stop.